Okay, in this lab, we're going to look at some of the features about how light behaves when it interacts with different materials. And specifically, we're going to be looking at a relationship known as Snell's law and another relationship known as the law of reflection. Now, the first thing that we're going to look at is the law of reflection. And that just basically says that when light reflects from a surface, it reflects at an angle that is equal to the incident angle. In other words, if I have a surface, for example, a mirror, I could imagine a beam of light coming in and reflecting from that surface. So if I come here at this angle like that, it's going to reflect at the same angle. Now, you may think, okay, that makes sense, and if I draw in this angle and that angle, those angles would be equal to each other, and that's true, but that's not actually how we define it. Because when you do optics and you consider how rays of light are interacting with different things, when you have a ray of light interacting with some material and it's interacting with the surface of the material, we always measure angles relative to the normal. Now, you'll remember from Physics 1 that normal means perpendicular. For example, we talked about the normal force. Well, what we're going to do is we're going to draw a line that is perpendicular to the surface, and all the angles that we're going to be talking about are drawn relative to that normal. So this angle that I've drawn in green here, that would be some theta 1, and that would be the incident angle, because the ray of light is coming in like this, it's reflecting from the surface and going like that. So it's incident on the surface coming in like that, and then it's going to be reflected like that. And then we would say that theta 1 is equal to theta 2. The incident angle is equal to the reflected angle. The incident angle equals the reflected angle. And that is the law of reflection. Now the next thing we're going to look at is what happens when air goes from one transparent material into a different transparent material. So, for example, you could have a beam of light coming in at some angle, and of course we're going to measure that angle relative to the normal, so that would be our incident angle. And what we're going to find is it passes from one medium into another medium. It does not go in a straight line. We would expect, if it were just continuing in air, a beam of light would just keep going straight. But what actually happens is that it's going to bend relative to that normal. So instead of going straight, it's going to come in at some steeper angle like that, and so it bends. And the refracted angle would be different from the incident angle. And so we would say that theta 1, the incident angle, and theta 2 is what's called the refracted angle. And the reason that it bends is because the light actually changes its speed when it goes from one material into another material. And as it slows down or as it speeds up, it actually bends. Now, one quick caveat, that's only true if it's coming in at an angle like that. If the light's coming in straight down, it's just going to pass through straight down. It only bends when it's coming in at an angle. And again, this bending process is called refraction. And so, in any case, those are the two things that we're going to look at in this lab. We're going to look at the law of reflection, and we're going to look at Snell's law. Now, Snell's law is the mathematical relationship that describes that, and we're going to look at that in another slide. But first, let's look at the law of reflection. Before we get there, though, I just want to point out one feature. There's two different types of reflection. When light strikes a surface, there's what's called specular reflection. And that's, you might remember that spectacles is an old-timey word for glasses. It comes from Latin, but basically what specular reflection means is that the law of reflection holds at the macro level. And so you have a bunch of rays of light coming in. You might have a beam of light, each of them having a bunch of parallel rays, and each of these rays is obeying the law of reflection. And so the beam comes in, the beam reflects off the surface, and throughout the whole beam, if I draw in a normal line, the angles of incidence all equal the angles of reflection. Now, on the other part of the picture, you can see that the beam of light is coming in, all the rays are nice and parallel, but they strike, and they go off at all kinds of different angles. And so you might look at that and say, oh, well, the law of reflection doesn't seem to be a very good law because it's not working there. But actually, it is. If you blow this up and you consider just a single ray, and I pick this ray here, and I draw the normal line for just that first ray, the angle of incidence and the angle of reflection for that first ray are equal to each other. And that will be true for every single ray that you draw. So at the individual points, so if I look at where this point is contact, the law of reflection for that single ray works. The law of reflection for that single ray works, and so on for each of these individual rays. But because of the roughness of the surface, the normal is not in the same direction at every point where a ray of light is striking. And so because of that, the individual rays scatter out. That's why most surfaces don't act like mirrors. They're simply not flat enough. But when you have a surface that's flat enough so that all the rays behave in the same way, the law of reflection is going to let you understand how the beam of light is coming around. So the law of reflection simply says the angle that you come in at equals the angle that you leave with. The incident angle equals the reflected angle. And again, all of those angles are relative to the normal. Not relative to the surface, but relative to the normal. Okay, to prepare for this lab, we're going to look at a simulator that we're going to be using to investigate the law of reflection and the law of refraction, which is also known as Snell's law. So, here is a picture that I've taken from the simulator, and I have a laser beam that is generating a beam of light, and it's striking the surface, and this is typically what happens when you have a transparent material. Let's say I've got air up above and I've got glass down below, and both air and glass are of course transparent. Now when the light comes in to the surface of the glass, some percentage of the light reflects. And you know this if you've ever looked through a mirror and it's bright out and you see your reflection in the pane of glass, so that you know that not all of the light coming from your face is going through the glass, some of it's reflecting back towards you. But only a percentage gets reflected and the rest of it travels through. Now, as we talked about Snell's law, which is also known as the law of refraction, the law of refraction is Snell's law, and that relates the angle at which the light is coming in and the angle at which the light is entering the material. So it's coming in at some incident angle. I can call that theta 1, and then it passes through into the material, but it actually bends and it's coming in at some refracted angle. So theta 1 is the incident angle, theta 2 is the refracted angle. And it turns out that there's a specific mathematical relationship between those angles, and that's Snell's law, which we're going to look at in the next slide. So here I have two different materials, and every material is characterized by something that's called the index of refraction, or I should say every transparent material is characterized by something called the index of refraction. And this value, the index of refraction, is given as c divided by v, where c is the speed of light in vacuum, and v is the speed of light in the material that you're talking about. In that case, this would be this kind of purplish material. What's the speed of light in that purplish material compared to the speed of light in vacuum? That would be, the ratio of those values would give you N2. So v would be the speed of light in the material. And by the way, the speed of light is always going to be, the speed of light in vacuum is always going to be bigger than the speed of light in some material. When light passes from the vacuum into any material, it's going to slow down. Of course, if the light is passing, say, from glass into the vacuum, then it's going to speed up. And so light is always changing speed as it's going from one material into another material. And actually, that change in speed is what causes the refraction. As it speeds up and slows down, it bends. And again, in order for it to bend, it has to be at some angle, not coming straight on. But once you understand what n is, it's very simple to plug it in to Snell's law. And so we're going to be investigating Snell's law in this experiment and some of the features of Snell's law and some of the consequences of Snell's law. Now, there is one feature that I want to mention about this picture. The way that this picture is drawn, you can see that when the light passes into the second medium, if it had gone straight, it would have gone out like that. And so the ray of light in the second medium has bent towards the normal. And that happens when the second medium has a larger N than the first medium. In other words, in this case, N2 would be bigger than N1. So for example, up above you might have air, down below you might have glass, and that would tell you that the index of refraction, that ratio here of the speed of light in vacuum to the speed of light in the material, the N2 is a bigger number than N1. And you know that because it bends towards the normal, because it's gotten, the ray of light in the second material has gotten closer to the normal. It's at a smaller angle. And how do you know that happens? Well, if you just plug in values, if you make N1 and N2 bigger or smaller, and you solve for the angles, you'll see that in one case it's always bigger, in the other case it's always smaller. But just to recap that, if the ray of light goes into a larger index of refraction material, it bends towards the normal. Now you could imagine the ray of light coming from the bottom and going up. It would actually bend away from the normal because you're going from a bigger index of refraction material into a lower index of refraction material. And so light is actually reversible. So if it comes in here and it comes through at this angle, if I send it out at this angle, it's going to come out at the same angle it would have come in at. The light is reversible, and this relationship will hold true regardless of whether this is the incident or the refracted. Now, before I talk a little more about that, I wanted to go over a couple of the tools that we're going to be using in the simulator. So our simulator has this laser beam, and if you grab the laser with your mouse, you'll see these little green arrows will appear. And then you can take the laser beam and you can drag it at different angles. And so that way you can change the beam's incident angle. It's always going to strike at the same spot right here, but you could set it to come in at 60 degrees or 15 degrees or whatever angle you want, simply by dragging it back and forth. Now, when you first load up the simulator, the protractor is going to be off to the left in the lower corner, and you actually have to drag the protractor and set it onto where you want to measure. And notice that on the protractor, there's this, in the center, there's this vertical black line, just a little tiny one. And what you want to do is you want to line it up with the normal line, which is this dashed line here, so that the protractor is properly centered and the protractor is symmetric about the normal. So now, once you do that, you can drag the laser so that it's at some angle, which you can easily measure. So if I look at this, this would be 30, that would be 40, 50, 60. So it's between 30 and 40. It's not quite 40. I would say that's 35, 36, maybe 37, maybe 38. But I'm looking at that. I would say that that's probably an incident angle of 38 degrees. And when I come out, I see the incident angle is the same, which is what I would expect. Now, what's interesting is that when the angle comes out, it has bent. And so I can measure the angle it comes out with very easily. Now, one thing that you can note here is that if this ray of light were coming straight through, that the ray of light has bent away from the normal. So what does that tell you? That tells you that this index of refraction in the white area is smaller than the index of refraction in the purplish area. But the main thing that I want you to see from this slide is just how to place the protractor and how to move the laser and set it at different angles. Now, if I wanted to measure, again, this refracted angle, it would be very easy. I'd just look at my protractor. I see 30, I see 40, 45, 46, 47. So that looks like 47, maybe 48 degrees, something like that. And so that would be the refracted angle. Now, in the simulator, there are controls to set the indices of refraction. That's the plural of index, by the way, indices. The indices of refraction, if you click on this little drop-down box, you'll have the option of setting the index of refraction to be air, water, glass, mystery A, mystery B, and you can do custom. You can also input the number directly, and you can drag it with this slider to different values. But we're not going to do that. We're just going to try to do some simple experiments and get this relationship across. But I just want to mention that there's two different controls because there's two different materials. And so I can click here and turn that into water, or I can turn it into glass or whatever I want. If it's glass and glass, then there's no different material. You get no bending at all. The rays of light would just go straight through. And if you want to play with that in your simulator, you'll see that it works. But typically what we're going to be doing in the experiment is we'll be setting different values for different materials and investigating how the light behaves going from one material into the other. And when you're looking at this, I just want to reiterate, because a lot of times people get very confused by this, the angles that we're talking about, we're always talking about angles that are drawn from the ray of light to the normal. So if I want the incident angle, it's going to be from the incident ray, the one that's going like this, and that angle is with respect to the normal. Now, if I want the reflected angle, the one where it's reflected from the surface and going back, that ray is going back up like that, and again, that angle is with respect to the normal. So that would be the reflected theta. And I could call that theta 1 and theta 2. I could call it theta I for incident and theta R for reflected. Whatever label you give it doesn't matter, but the relationship is that those two angles are equal. Now, if I'm looking at the refracted angle, again, I always draw it to the normal, theta. I don't draw it, from the ray to the surface. I always draw it to the normal. And that is an important detail to remember when you're looking at these. Now, one thing to note, again, this is obviously a situation where the light is bending away from the normal, so that means you're going from a bigger index of refraction, a larger N value, to a smaller index of refraction, a smaller N value. And so the ray of light is bending away from the normal. What's interesting, though, is that as I keep increasing the incident angle, as I make this angle bigger and bigger, this angle will also get bigger and bigger, and this ray will approach the surface there. So you can see here I've put the protractor on so you can kind of get a sense of the angles, and I've increased the incident angle significantly. And so the angle relative to the normal has gotten bigger. And this refracted ray, so there again, this is the reflected ray, reflected, and this is the refracted ray. And as this angle gets bigger and bigger, you can see that the refracted ray is approaching the surface so that eventually it's going to be parallel to the surface. And if you increase the angle beyond that, this ray will disappear completely and the light will be totally internally reflected. And that process is called total internal reflection. Now here we see I found the angle at which we get total internal reflection. So there's no longer a ray penetrating into the second medium. So again, this might be something like glass. This lower medium might be something like the air. And so I've found the angle for which no light penetrates into the second medium. It's all reflected internally, that total internal reflection. And as I increase the angle further, I'm going to get this angle is increasing as well, because the angle of incidence still equals the angle of reflection. But that ray that was formerly transmitted into the second medium is no longer there. And the minimum angle, the smallest angle that you can find that makes that true so that the light is totally internally reflected, that's called the critical angle, the smallest angle for which the light will be totally internally reflected. Now let's look at Snell's law. When you have Snell's law, you have n1 sine of theta 1 is equal to n2 sine of theta 2. And here we have n1 is the index of refraction for the incident medium, and n2 is the index of refraction for the medium in which the light would normally be transmitted into or refracted into. But here, because of the total internal reflection, the light does not pass through to this second medium. Now, to find the smallest angle is going to be the one for which the transmitted ray just bends to that 90-degree angle. Remember, the angle is always to the normal. So the transmitted ray makes a 90-degree angle. That's the point. You get bigger than that angle, it disappears, and you get total internal reflection. So that 90-degree angle is the one that's key. Now, the other thing to note is that when you have that second angle be 90 degrees, the sine of 90 degrees is 1. So that whole term turns into 1, and you end up with n1 sine of theta 1 equals n2. But at that angle, the angle for which you have 90 degrees, that is the critical angle. So typically we can say that n1 sine of theta critical, and we generally write that with a lowercase c for a critical angle, is equal to n2. Now, you can solve for the critical angle sine of theta c is equal to n2 over n1. And very often n2 is air, but it could be anything. The only requirement is that n2 has to be smaller than n1. Why? Because if it were the other way around, instead of bending away from the normal, the refracted ray would bend towards the normal, and you'd never get it going back into the second medium like that. But anyway, that is total internal reflection and the critical angle. Okay, in this slide we want to look at Snell's law, and we're going to be measuring actually the index of refraction of a particular medium. And I apologize, I accidentally put the wrong picture here. I wanted the one where the ray would bend towards the normal, something like that. But it doesn't matter because we're going to be looking just at the equations here. So here we have n1 sine of theta 1 is equal to n2 sine of theta 2. That's Snell's law. And we know that n is the index of refraction, and it's the ratio of the speed of light in the vacuum of space divided by the speed of light in the material that the light is passing through. Now, what we're going to do in this experiment with the simulator is we're going to take an unknown substance and we're going to measure the n value, and we're going to go from air into that unknown substance. Now, if we go from air, the index of refraction for air turns out to be just 1. And actually, it's the vacuum of space is also 1. But air is so rarefied, it's not dense at all, and so effectively the index of refraction for vacuum and for air is 1. And so if I say that the index of refraction for the incident medium is air, which is 1, I end up with a relationship sine of theta 1 is equal to n2 sine of theta 2. And what we're going to be doing in this lab is we're going to be measuring n2 by using the simulator to plot different angles. Now, I could, of course, just pick an angle like this if I wanted to, and this can be a good way for you to check your results, but if I just did a single angle, that would not be very accurate, and if I made a mistake, I'd have no knowledge of whether I made a mistake or not. We know that when we do experiments, the more data you take, the better it is, the more confident you are in your results, and the lower your relative uncertainties will be. And so a better thing to do would be to take an average of these values. But again, this can be tedious if you're doing it for a lot of data, and also it doesn't really visualize what's going on as well. So one thing that we have done time and time again, we want to represent data and understand trends and understand relationships, is that we graph the data. And so that's what we're going to do in this experiment. So you guys, I'm going to give you a bunch of incident angles, theta 1, and you're going to set them up, and you're going to measure the refracted angle, which is the angle to the normal line again, and you're going to find theta 1 and the corresponding theta 2, and you're going to plot them. Now, if you look at this equation, sine of theta 1 equals n2 sine of theta 2, that looks like y is equal to mx. So if I plot sine of theta 1 versus sine of theta 2, then I should get a straight line, and the slope of that line should be the index of refraction of the material. And so again, remember that n is just the speed of light in vacuum divided by the speed of light in the material. So that's all the n is. The n is just, it's basically a normalized speed. It's telling you how fast the speed of light is in that material relative to the speed of light in the vacuum, which is its maximum value. But by plotting them in this way, you'll get this straight line, which represents an average of many data points that you can consider a really effective way of calculating the n. And so in the lab, you'll see there are some instructions on how to do that, but that is one of the goals. So in the simulator, there are these mystery materials, and I picked one for you, and you're going to tell me what the index of refraction of the mystery material is by giving me that plot. And that is basically what we're doing in lab this week. And so that is what we'll be doing this week.